let me share my screen. Let's see.
A nice meeting we had yesterday. Very interesting.
Yeah. Thanks, Sid.
Now summing it up and saying, okay, what did it tell us?
Okay. Are you able to see my screen?
Yes.
All right, excellent. So I'll just make a very quick announcement and then we'll let Leen take from it. Okay, let me just too many buttons. It's okay. I'll just do it this way. All right. So good morning, everyone. So as I said, it's going to be a few announcements before we begin our seminar this morning or afternoon if you're overseas. So first of all, if you're interested in submitting an abstract to 59th US Rock Mechanics Geomechanics Symposium, the deadline has been extended to November 4th. So you have a few more days to submit your abstract. So it's going to be in Santa Fe, New Mexico in June 2025. The second announcement is about Hydraulic Fracturing Technology Conference. So it will be on February 4th to 6th in 2025 in Woodlands as usual. And so, and this year we are going to have a special ARMA session called Highlights from American Rock Mechanics Association, and we already have speakers lined up. So if you're curious to see what's the latest and greatest at ARMA, they're going to be at least the one that's going to be presented at HFTC. You can check the HFTC program, and we also encourage everyone to consider attending this great conference. Right, so registration is open right now. And now to last but not least, well, I don't do introductions really often. Actually, last time I think I forgot to introduce the speaker. So this time I made it bulletproof. So now we have a we have a slide. So we have pleasure today listening to Dr. Leen Weijers from Liberty Oilfield Services. So Leen, he's VP of Engineering at Liberty Oilfield Services and served as its business manager at Liberty's founding. So he worked at Pinnacle Technologies from 1995 to 2011, where he oversaw development of a commercial fracture growth simulator, Frac Pro PT. So Leen has authored dozens of publications and contributed a chapter to the recent SPE hydraulic fracturing monograph. So Leen completed his doctoral research at the Faculty of Mining and Petroleum Engineering at Delft University of Technology in the Netherlands. And so today he's going to speak about a very nice topic called making unconventionals competitive, minimizing the cost per barrel oil. So now I'm stop sharing. So everyone, please welcome Leen. And so if you can share your screen, and now the floor is yours.
Yes, hello everybody. Give me 1 second so I get the right screen here. It should be this one. Can everybody see that presentation mode PowerPoint?
Yes.
Yes.
Thank you.
All right. Well, thank you so much for having me, and Igor, thank you for the introduction, and Eric for the logistics of setting everything up, and thank you for having my talk here. It's this talk is actually a talk I'm doing for the SPE in their what they call their distinguished lecture program, and so it's been vetted, I hope, and what I've set aside, in talks with Igor and Eric, about 40 minutes or so of talk. I've set my timer. That's already clicking at 39, and have about 30 or so slides for you that I want to go through, and hopefully there's enough time for questions and things like that. But the presentation title is Making Unconventionals Competitive, Minimizing the Cost per Barrel Oil. Let me just see here. All right. Quick introduction, then I'll dive into kind of a competitive cost metric for our industry, but a very simplistic one. I just want to dive into how we can minimize the cost per barrel of oil. And it's straight that, no net present value analysis, no fancy economics. And I want to just look at the trends of what has our industry done in shale to improve or increase the barrels of oil production and to reduce the cost, especially when it comes to drilling and completions. And then, of course, we look back at that ratio, the cost per barrel of oil, and how that has evolved, at least in shale reservoirs. I'm not really talking much about conventional, but how it has changed in shale and how it has really changed the rules of the game and has a big impact on the world. All right, I'm stepping back, quite a bit for many of you. Many of you know, of course, what hydraulic fracturing is, but I want to just explain in one slide for those of you who don't know it, what the difference is really between conventional and unconventional fracking. And it's a little bit of a history lesson, if you will, but also with physics involved. So if we look at, say, layer cake geology that's laid down, say, on an ocean floor or something like that, different environments, shales, sands have been deposited, etc. Now, shale typically is laid down on the ocean bottom, and typically a lot of plankton dies, as really small particles are far away distributed toward the ocean, typically from a river or something like that. But you have a very continuous, typically, strata, and there's maybe some organic content, maybe a fraction of a percent or a few percent organic content that, as layers are, deposited on top of that, Mother Nature is putting it in its pressure, in her pressure cooker, cooked at high temperature and high pressure, and that kerogen, that organic material, mostly plankton, is slowly turned, when it's just cooked right, into oil, and when it's overcooked, into natural gas. So what happens with that oil and natural gas over millions and millions of years of that deposit history is that some of it is expelled from that shale and actually accumulates into traps, into typically higher permeability and higher porosity rock. And that's where, that was our early target for fracking and production. These traps that have accumulated resources, where oil and gas is being gathered and highly concentrated, if you will, that's an easier target. So since hydraulic fracturing was invented, and this is more than 75 years ago, actually 75 years ago is the birthday of commercial fracking that Halliburton did in 1949. But it was first done in 1947, again targeting higher permeability sandstones, concentrated oil and gas. And really what happened with hydraulic fracturing, and I won't dive into the details of how it works, but hydraulic fracturing can help mine, say, hydrocarbons hundreds to thousands of feet away due to the higher permeability of these typical sandstones and carbonates. And I'm highlighting a range there, maybe from 0.1 to 1,000 millidarcy or a Darcy type rock. So hydrocarbon molecules can flow to a conductive fracture to be produced. But of course, shale is the source rock, and shale is highly abundant. There's lots and lots of it in the world, way more than sandstone and carbonate. Its permeability is, orders of magnitude lower than your typical sandstone and carbonate. Sometimes, maybe 100,000 times or maybe even a million times lower in permeability than some of these high perm sandstone carbonates. So the strategy, oil and gas doesn't really flow to a fracture if we would treat it in the exact same way as in a vertical well, single stages, that conventional jobs often are. So instead of that, you need to bring the frac to the hydrocarbon molecule. And that means you create surface area or kind of a radiator type fracture, or 2 miles of plumbing, as my CEO, Chris Wright, often says. And for that, the recipe is that you create fractures with lots and lots of surface area. And just by accident, after targeting this for a long, long time, this secret was actually unraveled by Mitchell Energy in the Barnett Shale around the end of the 1990s, early 2000s. They tried 30 different wells with various different frac designs. And a colleague of mine, Mike Meyerhofer, suggested to the completion engineer over there, why don't you try slick water? It's been greatly successful in these tight sandstones. It encourages complexity in fracture growth due to its low viscosity. There's lots of downsides, but why don't you try that? And you create more surface area that way. And we actually observed this with just at the start of the birth of microseismic mapping for fracture analysis. We also saw this complexity in network. Maybe something typical for the Barnett Shale, where it really encourages complexity in fracture growth. But there's things in your frac design that you can do to encourage that complexity, even though the complexity in fracture growth may not be as high as in the Barnett Shale. But the key is really creating surface area, creating that inverse radiator that attracts lots and lots of oil and gas molecule flow from the rock. So that's the difference between conventional and unconventional fracking in a nutshell, with a little history lesson. And I'm going to talk more today, over the last 15, 20 years of what has further been done in these unconventional rocks to advance oil and gas production and make economics better. That's where I get to this very simplistic graph. There's a fine line between the numerator and the denominator, as per Yogi Berra, great mathematician. And if we draw that fine line, I'm going to talk about each of these different components in this talk. So when I talk about barrels of oil produced, I often just talk about the 365-day production response. As a service company, I'm on thin ice when I start predicting what EURs of wells are, ultimate recoveries of wells are, because that relies on models. But what I want to do is all the data I'm showing you is mostly 365-day production when it comes to production. And the nice thing is we have lots and lots of lots of states actually require disclosure of that, and we have hard data to prove what that is. So it's measured data. That's the benefit of that. It's not very short-term production. It's a little bit longer, and often it's a very good predictor of what a well will do in 5 years or 10 years, or maybe even its ultimate recovery. And of course, it's impacted by frac design changes, by changes in geology, by well interference, and all kinds of other things. And then drilling and completion costs impacted by technology advances, efficiency gains, and of course, together, we work on minimizing that cost to produce a barrel of oil, and that is achieved by reducing cost and improving production. All right, I'm going to talk a little bit about, you see in the left top corner, I'm going to talk about barrels of oil. A couple of slides on just the numerator, if you will, or the denominator, I'm sorry, of the little equation we saw. And really, many of the fracture design considerations that we are still, working through today in our industry in unconventionals is to make that radiator denser and larger. So to make the fracture network larger and denser. And of course, a way to do that is to drill horizontal wells that become longer and longer. And you can see here in this graph, this is all the way back, again, since the dawn of hydraulic fracturing, more than 70 years ago. In the US, these are US wells that are fracked, or out of all the wells that were being drilled, if you will. So focused on the dashed lines, there's a dashed line in orange. That's the fraction of vertical wells that's being fractured. And then the dashed line in blue, horizontal wells that are being fractured. And you can see that we are nearing 100% of all these wells. Almost every well in the US today is fracked, 90 to 100%. And you can see also, of course, we had large number of wells drilled in the 1980s, early 2000s, with the start of the shale revolution, especially starting in natural gas. But today you can see we're almost exclusively drilling horizontal wells as well that are almost all fractured. And we can actually handle quite a bit of fewer wells, if you will, and still have the record production that you see today in oil, gas, and NGLs. All right. What else affects the barrels of oil produced? And this is a very busy slide. Now, don't necessarily look at all the data, but look at the trends in the data, if you will. And there's different things that we do to, again, increase the density of fractures and increase the size of the total network that we're creating. One way, and of course, we're doing multi-stage fracking. If we increase the stages and distribute flow to a smaller area, that is often a thing that points production in the right direction. So you will see overall for all the wells in the US, stage count has increased. That's not only because we do longer wells, but also because we are shrinking the size of a stage, or at least have done that for some time, to more target production to create that density of fractures. So higher stage count per well. We're pumping a lot more material per well. Typically in the past, and this is over, the graph looks at about 11 or so years. Typically sand volumes have increased from about 4 million pounds of white sand to today mostly 20 million pounds of local sand. Water, pumping a lot more water, typically slick water or light gel, and today mostly slick water, about 400,000 plus barrels per well. Injection rate has increased on a per stage basis from about 40 to 100 barrels a minute. Impact for a service company like Liberty is that we bring a lot more equipment, horsepower, pumping power to location for the work that we do today versus what it was about 10 years ago. And of course, the resultant of that, what we're interested in, barrels of oil produced in the first year, for a typical US well has increased from 60,000 to about 160,000. And as you see from these violin plots, of course, there's a large distribution, but the averages are definitely up significantly by about 2.5x. I want to show a couple of small examples of that production improvement. And this is really, this graph that I'm showing here, with cumulative production over a 10-year period. This is kind of the idea where Liberty Energy got started in North Dakota with that same design or a similar design that was done in the Barnett Shale, but now in an oil reservoir, where we wanted to give slick water fractures a try over the at that time dominant design of sliding sleeves, cross-linked gel, and sand. Sliding sleeve and cross-linked gel are great designs for service companies, because service companies can get their efficiency up. They can frac all the time. So a well can be done very, very quickly. Cross-linked gel is a great way to sell chemistry. And of course, when you're pumping at a relatively low rate, that is a necessity. But it's not really the best we found in this particular case for the reservoir to create that density of fractures. And especially with sliding sleeves, no well-defined injection point in the well makes it tougher to control where fractures are growing and how many fractures you get. So we decided that to give a plug and perf design with slick water, and in this case ceramics, a try. And I think especially due to the kind of the creation of perforations, the distinct points along the lateral where we create these perforations and fractures, slick water in larger volumes with higher rates, more material, you can see the impact of that. And you see the impact of that today is similar to the impact we saw maybe in year one. But 10 years later, these trends are still very, very, very much there. And of course, after 10 years, average production from this red design in plug and perf, slick water, and ceramics, about 500,000 barrels versus only about 200,000 barrels for the conventional design that was pumped there more than 10 years ago. And these, of course, these trends seem to be continuing, strongly. And this is all, just to draw attention to the little map, this is all done in an area that's about 10 by 10 miles with relatively little reservoir variation, but you can see the impact of design changes is profound. And similar, our industry has done similar things in all kinds of other formations. Now, you can't really read the formations very well in this particular case, but these are all the high, the targeted formations in the lower 48, if you will. And you can see, again, the 365-day production response all the way back from 2010 till just last year. And you see that significant improvement in both the production per well, that's up significantly, more than 130%, but also the production per foot in these laterals. Because you could say, the upper graph, well, longer laterals are responsible for higher production, but the per foot, the density kind of component of it is also up about 50%. Oh, sorry. All right. Moving on, a little bit on the dollar side, if you will. One of the things, and my colleague Ben Poppel, our director of field engineering, often says, we've traded in our industry viscosity for velocity. And what he means with that is that we've lowered the chemical contents besides water that we're pumping in a frac job. We don't need that higher viscosity to carry proppant in the wellbore into the fracture, but we carry it with the higher rates that we're pumping at. And on the top graph, you see over that last decade or so, how rates have increased from again, about 40 to 100 barrels a minute, and that's still going up. But also the chemistry, for instance, gel concentration that you see on the bottom graph, you see that small vertical line, there's a big distribution of data, but you see the averages on this plot also with the small horizontal lines, definitely going down. We're pumping less gel, more FR, friction reducer in slick water jobs with more and more, fraction of all chemicals pumped water. Another reason for reductions in cost is pumping local material. Now, what I'm showing you here is the mesh size, but that's often a proxy. White sand and ceramic, maybe initially in the first decade or so, or early on the left-hand side of these graphs, you see we're pumping larger material, 20, 40, and 30, 50 mesh proppant, mostly coming from Wisconsin and Minnesota, white sand, monocrystalline. And as you can see here on the bottom, the smaller type sand are typically local sands from either local mines or even today, scooped up near frac locations, especially in West Texas. And you can see that's the dominant well count. The bar size is the well count. And you can see more and more wells in the US are done with this finer material, which also invites the lower use of chemistry. It's cheaper because we don't have to transport proppants for 1,000 miles from Minnesota and Wisconsin to Texas. We can scoop them up local and put them in a truck and just drive 10 miles with them instead of, the 1,000 or more miles that this proppant went through before. All right, more on the cost side, and let me check my timing. Okay, good. One of the things as a frac company, and this was initially, of course, driven by, say, the sliding sleeve designs, is service companies want to be busy pumping because that's where we make our money. So if you're doing a plug and perf job that I showed you earlier on in the Williston Basin, especially if it's single well, there's a lot of downtime in between. But of course, as an industry, we have minimized that downtime because we're doing 2 wells at the same time. We're doing a dance with wireline, where wireline perforates and plugs one well while the service company, the pumping services company, fracks another well. And then we change chairs, if you will, and do it all over again all the time. So it's really improved how much of the time we're fracking. And if I look at a Sankey diagram that I showed you here, kind of the vertical side of it is 100% of all time, 100% of time in a day, in a month, in a year. And when I started in our industry more than 30 years ago, of course, when you were on a typical frac location, there were exceptions, but you were probably fracking a few percent out of every hour or every day. Well, today that number is over 50%. So 10 years ago was maybe 35 or 30% or so. But because we are always, there are always reasons for not fracking due to scheduling, moving, third party and non-pumping time for rigging up and rigging down, for example. And there's of course downtime. Things break and we have to stop, and that's something that has to be addressed. So today, about 50% of all time is frac time. But of course, where we want to go is to even increase that portion of the time that we're fracking, because we can kind of earn back our sunk cost with more time while pumping. There's many different things that have been done around the frac location to improve that. There's not just one thing that's responsible for pushing that pump time from about 30%, back 10 years ago to over 50% today. It's really driven by all kinds of components that we've made better. And if I can just take maybe one brief example, this is a frac location that you see, modern frac location in the DJ Basin, just north and east of Denver. Excuse me. And in the bottom right corner, I'm showing you containerized sand. Now, this is very different from how sand was delivered to location 10 years ago. Somebody had the idea to put it in boxes, and a revolutionary idea for really sand. And it has really helped. You can see over there the forklift just above the word sand. Forklift moves these boxes, and actually trucks with 2 boxes on them come to where we are actually standing as observers in this picture, and the forklift takes them off. Now, 10 years ago, air pressure was used to offload proppant from trucks or into silos typically, or into bins that were stationary. And took a long time, may have taken 30, 45 minutes, very noisy, very dusty, not pleasant to work around, created a lot of dust around location, and of course for neighbors around location. And that's all eliminated in this very efficient system where 1 or 2 boxes can be offloaded in a fraction of or in a matter of a minute or two. And the truck can be moved out, and it's a very efficient process. And a lot of these changes, that's one example, but there's all kinds of other things associated with all these components that I'm highlighting that have improved. Resulting in a smaller footprint, higher redundancy of materials on location and parts on location, more efficient delivery, reducing fuel and emissions. I'll talk a little bit about that in a bit. Extended lifetime of equipment. So many other benefits associated with that. 2 more things I want to highlight that are on the dollar side. So modern and efficient frac operations. One thing I want to highlight here, the picture on the left shows high pressure hoses. Farther on, this is a rig up, of a frac location. We're looking toward the blender. We're standing where the well, near where the wellhead is. But this is actually a rig up with high pressure hoses where on the left-hand side, the frac pump is connected to what we call the missile, or the line that connects, the high pressure equipment to the well. So these high pressure hoses have a more extended life. They're more expensive, but they last way longer and are easier to work with on location as long as you have a crane available. And they replace, what you see a little farther down that line, the fixed iron with multiple connections, and it just has a higher survival rate, if you will. Another thing that you see on the right-hand side, you see the backs of various quiet pumps that are rigged up to a monoline in this case. Now that monoline used to be multiple smaller lines in the past. And we're standing here as our viewpoint is above the blender, and we're looking toward the wellheads, a couple at the very top of the picture. And but you can see that just a single line connects all these pumps to the wellhead. And while it's beefier equipment and all that, it also lasts quite a bit longer and doesn't require as much maintenance. Next example I wanted to show, this is a busy table, but maybe just focus on the top two lines. And you know, about a dozen or so years ago, most equipment in fracking was tier 2 or tier 4 equipment, and all run on diesel, 100% diesel. So the thermal efficiency of that baseline that I'm showing you, the first column, about 36%. Why is that important? Thermal efficiency dictates how much fuel you need to get a certain amount of work done. It's kind of how much of the chemical energy within diesel can be turned into mechanical energy. And you want that number to be as high as possible. You can see on the right side, currently, you know, and many different service companies have different ways to burn natural gas. We've chosen for gas recip engines. So they burn 100% natural gas. Their thermal efficiency is 43 to 44%, significantly higher than a gas turbine even. And of course, that results in, you know, less fuel needed. And the fuel that is needed then is only natural gas, which has which cuts CO2 emissions by about half for the same amount of material used. So you can significantly save on fuel. And why is the change to natural gas important? Because natural gas, the price for natural gas on a per energy unit basis is about 3 to 5 times lower than diesel. So of course the driver to change these engines and move to just natural gas burning equipment is that, you know, it's significantly cheaper to do so. If you think about fuel consumption being about 1/5 of a fracture treatment job cost, and you can almost eliminate that cost, you have significant savings. It also helps, it makes our equipment, the power density on location higher, it reduces emissions, and there's capital efficiency in it as well, because the cost to build it per horsepower is actually lower than building past equipment. So a couple of trends for pressure pumpers, if you will, here. And I'm just looking at changes in this graph since 2012. And what I just want to show you, and sadly on the bottom line is a revenue line. So what that means, I'm showing this metric per frac fleet. So there's about 250 frac fleets running around the lower 48 in Canada. And you can see the revenue per fleet on, say, a year or a monthly basis hasn't changed that much. But look at how much more work that fleet has been doing. It pumps at a higher rate, pumps against a higher pressure. Pump time, you know, per fleet is up significantly, as you can see from some of these curves. Pump time is up, you know, about 100%. But in that pump time, we're pumping, you know, about 400% more proppant and slurry, and we're doing, you know, 500% more horsepower hours. So that's actually the work done by these pumps. So you can see tremendous increases in throughput, if you will, not just per time, but also in kind of a rate sense. And of course, you know, what it has done, what I'm showing you here is a comparison of what a typical oil and gas operator earns versus what pressure pumpers and drillers earn. And I apologize, there's lots of lines in this graph, but pressure pumpers and drillers are the lowest two lines in the graph. And this is the cost to that actually, or the revenue pressure pumpers and drillers get from fracking and drilling 1 foot of lateral. So you can see that's in the, couple $100. Of course, as a frac company, we spend, about 30 seconds to frac, a lateral foot, if you will, equivalent. And you can see that revenue has been going down relatively steadily. We're currently at about $200 or so per foot. Of course, our customers, they take the risk of commodity pricing. And of course, when Saudi Arabia declared war on shale at the end of 2014, you can see that the revenue they had from a foot, the barrels of oil that a foot of lateral produces in a year, their revenues were down significantly. But you can see the opposite happened, when Russia declared war on Ukraine. Several governments were popularizing the Just Stop Oil movement. And of course, oil prices spiked to, unfortunate consumers. And you can see that differential between, the earnings from a lateral foot versus, revenue by drillers and frackers has never been bigger than 2022. So lots of things happening in the industry. One of the things that I'm proud of is that, our oil and gas industry is just extremely efficient. If you look at our entire energy use in the United States, this is in 2021, a graph from the EIA. These are, for total energy, we as a country require about 100 quads. That's 100 quadrillion British thermal units, BTUs. And you can see where these 100 quads are coming from, and about 65 of them are coming from oil, gas, and NGLs. Of course, there's another 10 or 11 that come from coal, but our industry, with about 350,000 workers, is responsible for 2/3 of all that energy. And you can see more workers actually build windmills and solar panel parks, and the amount of energy they produce is about 13 times less. So that amounts to the fact that an oil and gas worker produces about 17 times more energy than a renewable energies worker. And that's not, of course, insignificant. All right, and that's, of course, why the cost of our services have come down. The cost per well for our customers has come down. Over the last decade and a half or so, you can see over the last excuse me, over the last 2 or 3 years, costs have come up a little bit. So if you look between 2011 and 2023, maybe the change is not that dramatic, but of course the trend has been down, and actually is continuing to go down in 2024. But now let's combine these two things as per Yogi Berra, his ratio. So you've already seen the two graphs on the left. The cost per well, again, from 2011, it's maybe about 15% down. Production per well since 2011, about 134% up. Now I combine these two, that's your dollars per barrel. Oh, sorry. So that's your dollars per barrel, dollars on top, barrels on the bottom. If I divide by, or use a division, I'm getting the cost per barrel of oil, and that I show on the right-hand side graph. And I'm also showing, and the different colors in this graph are for different basins. So for instance, blue is the Permian Basin, red is Williston. And you can see for all these basins, the dollars per barrel, and again, that's per 365 days produced barrels. That is down significantly. Now, if I also plot WTI price on there, the West Texas Intermediate market price, you can see, when the WTI price is roughly, is lower than the dollars per barrel, that I get from these different basins, then that means that I got a break even that's maybe approaching 2 or so years. Today, the dollars per barrel for different basins is actually lower than WTI. So that means that break even with my very simplistic dollar per barrel oil metric is actually less than 1 year. So that's how you become competitive, of course, when that price is down substantially. We just check on the timing again. I want to skip maybe the next couple of slides. It's a little bit analysis based, and you know, Igor, I will share this slide deck with you. So if anybody's interested in the deck, I will share it. But in the interest of time, I want to just maybe skip through a little bit of this here, some of the analysis that we do to kind of lower that cost per barrel of oil, and how we use statistical evaluation of publicly available data to kind of hone in on optimized parameters for fracking. I just want to maybe talk a little bit about the consequences of kind of this competitiveness in US shale. So here's a graph that shows all primary energy produced by the US, not consumed, but produced. And you can see, of course, since the shale revolution started, about 15, maybe a little bit longer ago for natural gas, but how our energy production has exploded. And this is again in that quads metric, and we end, currently at about 100 quads on the very right-hand side of the graph. 72% of that is oil, gas, and NGLs, and about 84% fossil fuels. And that 84% fraction is about the same as in 1980, so it really hasn't changed that much. But if you look at growth over the last decade, production growth has been close to 3%. Renewables have kept up with that growth roughly, but on the number 1, 2, and 3 spot on the podium are NGLs up more than 9%, oil up more than 6%, and natural gas up more than 4% in the US. You can see that gas, oil, and NGL components back to the conventional wells and now unconventionals from shale since the year 2000. You can see, of course, since 1970 or so, we've been on a decline of production of conventional natural gas, oil, and NGLs, as you can see on the left-hand side of the graph. And these trends seem to continue. But of course, shale oil and gas have increased quite dramatically, and currently make up about 80% of the US production, and that's growing. All right, a couple of words on other impacts here while I stop my clock. We're almost at the 40-minute point, and I'm on one of my last slides. So of course, one of our goals, as a service company, as operators, is to bring oil and gas to customers. We want to provide, abundant, cheap, and reliable energy to everybody in the world. And there's quite a discrepancy of how much oil and gas and energy everybody has access to, due to, of course, many different circumstances. But one of them can be, high energy prices, and I think lower energy prices can be, help prosper, the world's poor, help make the world's poorest prosper, if you will. So what I'm showing in this graph is I ranked every country in the world cumulatively. I ranked them from the poorest energy, having access to very, very little energy, to having access to a lot of energy. And actually, there's orders of magnitude of changes between these. And I've actually put it in context of how many gallons of propane is a person using on a daily basis. Now, if we start on the right, the US is pretty far on the right, and you can see on the bottom scale that's 8 billion people on this planet. So very few people of these 8 billion people are on the far right, where they consume, in the US, about 7.5 gallons of propane every day. Think about it when you're looking under your barbecue. There's a 5-gallon tank. For all your energy purposes, every day, every American uses about 1.5 of these propane tanks. And of course, it's in different components than propane, but I'm bundling everything together in something that you can relate to. And in Qatar, that's actually even higher. That's almost like 20 gallons of propane a day per person. But if you look at some of the poorest countries in the world, that's only 200th of a gallon of propane every day, and it's mostly, of course, for food. And if you look at how, of course, these people live, they use for cooking purposes, they use wood, dung, and sticks. A very unhealthy environment where lots and lots of particles are released from burning, especially indoor cooking, resulting in the premature death of about 3 million people every year due to kind of these very unfortunate cooking circumstances that they use, just because there's nothing else available. Of course, for transportation, they use their feet. Sanitized water is hard to get. But as we go farther, and these are graphs actually from Hans Rosling's book, Factfulness, that I really like. But as we go to, more energy availability and richer people that actually have access to energy, of course, one of the biggest changes right there is on the bottom right, a propane stove, instead of using that wood, sticks, or dung, and way cleaner in cooking and helping to prevent these 3 million deaths every year from PM2.5, these very small particles that float around, get lodged into people's lungs, especially women and children that are near the cooking stove. And they die early, unfortunately. And as we get richer and richer, of course, we have different means. And then, of course, the very richest among us often tell us how all these other people have to live their lives energy-wise. But what I really want to focus on is that, especially with the U.S. shale revolution, we're producing as a country way more propane. We can help, kind of, especially with that problem on the bottom left, if you will, get rid of this extremely dirty, deadly cooking that still about 2.5 billion people in this world are using. All right. Of course, the U.S. has had a tremendous story and Canada, of course, as well. There's other countries following in our footsteps. Argentina has been very successful in the Vaca Muerta to drill similar and frac in a similar way as we have in the U.S. with likewise production results. But there are many other countries in the world that have significant gas reserves, significant oil reserves that can actually benefit from kind of the type of movement we went through in the shale revolution. If only, of course, and you can see here, this is on a logarithmic scale. U.S. proven gas and oil reserves are kind of mediocre if you compare it to some of the other countries in the world and their available reserves, if you will. Of course, what we need for that is political stability. We need freedom. Economic freedom is often tied to, helping that development. I won't go into the details of that, but of course, that limits today, where the shale revolution can be taken next. So in conclusion, I've taken a little bit more time, I think, but North American shale revolution has transformed world energy, and the technological changes continue as our industry finds better ways to minimize dollars spent to produce a barrel of oil, and that's through frac design changes and efficiency gains. And of course, the economic and humanitarian benefits of the shale revolution are massive, and I sincerely hope that the unlucky 7 billion people will find some way to benefit from it. That's all I have. Igor, back to you. Thank you so much for your attention.
Thank you so much. It's excellent presentation, and we have quite a lot of questions. So let's see if we can. Let's get started, right? So the first question is from Zeno Philip. So the question is production more sensitive to increase in proppant mass or increase in fluid volume? So any trends observed?
Hey Zeno, thanks for the question. Good to hear from you. I hope you're well. But that depends. I'm not going to give you a straight answer, unfortunately. We have seen in certain areas that, if permeability is lower than average, if you will, in some shale reservoirs, I think there could be a more sensitivity to the volume of fluid pumped. And I think if permeability is slightly maybe on the higher side, we sometimes see that even in the DJ basin where you have rock properties changing, it might mean that, you know, there's more of a connectivity focus than a surface area focus. So where proppant matters more in these slightly higher permeability reservoirs, but it's very hard to tell. And unfortunately, with the statistics, very often there's what is called collinearity between fluid pumped and proppant pumped. What that means is that we all, as frackers, change things at the same time. And when you're changing things at the same time, you cannot tell if one particular parameter is responsible for the production or the other. Now, there are, of course, for example, in the DJ, there are customers who pump more proppant laden, heavy fluid, higher proppant concentration. So maybe you're able to see a little bit of that. But often in analyses, there's collinearity between these parameters. So from a statistical perspective, it's hard to identify which one of these two is responsible. Overall, you can see bigger is maybe better, but what should be bigger, or should we scale them in kind of in tandem with each other, as we often do? But yeah, I think that's where, if there's variety in the statistics, you can maybe say a little bit more about it. But that's not often an easy one.
All right, thank you. So the next question is from Ed Sibritz. So his question is about slide 9. So how does the result change? So essentially, if you normalize it by proppant intensity.
All right, Eddie, good to hear from you. Slide 9. Okay, let me go back. I think it's this one, right, Eddie?
Correct.
All right, so, and the question was about proppant intensity?
Correct. So what if you normalize this result by proppant intensity? So
I see.
Intensity.
Yeah, that of course changes the game quite a bit. And of course, because I think, overall you can see, we've pumped 3, 4, 5x the amount of proppant per well. So yeah, it would normalize, it would lay these red lines and green lines more on top of each other, of course. But of course, the point is, what is the absolute amount of oil that you get out of it, and what the cost of the proppant is. Yeah, there is probably slightly higher amount of money you need to pay for more proppant. But often in North Dakota, when we changed from one design to another, again, production improved 2.5x or something like that significantly, as you can see in this particular example. And the cost went up maybe 1.5x or something like that, if I keep it in simple multipliers. So in my mind, that's always worth it, right? If you spend a little bit more money and you get more than that, relative amount in higher production, that's a winning case, and that's what you see in this example.
All right, so the next question is from James Rogerson. So is the trend moving towards the use of HVFR right now?
James, good to hear from you. Thank you for the question. For some operators, it definitely is. HVFR has a benefit that it has some carrying capacity. If you're pumping your FR at loads that are 5 to 10x what you need for proper friction reduction, you have a single chemical that can help you get to maybe single-digit centipas in viscosity, helping you carry it. Of course, there's still a movement to go to higher and higher rates, maybe not per well, but definitely per frac fleet. So I think if our operator partners can get away with using a lower concentration, they will do it because it impacts their cost side. But I think in cases where you have some tightness, where you may screen outs may be lurking, etc. It's nice to have that single chemical, if you will, to just dial it in and increase it to maybe avoid a screen out, and hopefully that's enough. Yeah, I think in general there is more movement toward FR. I think gel is used maybe just as insurance for very early stages, but I think ideally not used anymore, except for maybe places where water is scarce and expensive, and so there are other trade-offs. But I think in general there's more movement to FR, and where we can get away with it, I think we use less of it too.
All right, excellent. So then there are two more questions from me actually. So the first one is, so you mentioned that you have about 95% of horizontal wells are fractured. So why not 100%? What's the use of the of this? There's 5% which are horizontal wells which are not fractured.
And I do not have a good answer for you, Igor. I'm puzzled. I think it's actually still quite high. That these unfractured wells, but I think it's also a bit of an artifact of the fact that I'm merging different databases together. So I think that's right in the noise, that 95%. I should have said that during the graph. So I think there's probably a little bit of a mismatch in what that is. But I'm sure companies like Enverus, Rystad, they can dive into that better. But they also typically have models for these kind of things. And I do not know the full answer there, unfortunately.
Okay, thank you. And the second question is that, again, you show this trend like over the last 10 years that there was roughly a 5x increase in sand and fluid, but it was only roughly 2.5x increase in production.
Yes.
Does that mean that efficiency is actually down by 50%? And if you think about efficiency per fluid and sand, unit of fluid and sand pumped.
No, and that's fairly normal, Yeah, you wouldn't expect a 1-to-1 ratio, and here's the reason. I think a very simplistic reason why. If we make a fracture, we put twice the amount of volume in a frac, right? Mm-hmm. We pump twice as long, everything 2x, if you will, right? The length, height, and width are not going to increase 2x because that 2x volume needs to be distributed over these three different dimensions. So what you often see is that maybe depending on how kind of elliptical a fracture grows, maybe all of these, when they're all equal, they go up to power of 0.33 to the volume increase, right? So and if you're if you're stimulating a specific zone that is a fixed height, you're just growing the length. Maybe you're only getting a 30% benefit from the length portion if it's all conductive and everything else stays the same as well. So I think it's never a one-on-one relationship, but where of course you get your gain in higher permeability rock, conventional rock, maybe you get your gain from the width portion of it, right? So where you get more connectivity and less of a bottleneck for production response. But all these things change, depending on the height of the formation you're covering, how far out do you get proppant and things like that. So there's certainly diminishing returns. If you do that 10x and you're only getting 2x more in length, height, and width, total, or 8x volume, if you will, then you get diminishing returns. And that's also why at some point maybe it's better to drill another well instead of doing a fracture that's ever and ever larger. So that trade-off comes in due to the fact that dimensions are, not a one-to-one relationship with volume.
Thank you. So the next question is from Joe Franz. And so his question is about proppant and in particular about conductivity of local 100 mesh sand. How does it compare initially and over time with white sand?
Yeah, Joe, good question. Good to hear from you. Yeah, of course, it's not very good, but the key is it's good enough. And so, yeah, you don't often hear that, when people are in their career or whatever, it's good enough. But for proppant, it really matters, kind of that threshold of good enough, because it's an economic trade-off then, right? And the fact that, if the connectivity is, say, 10 times lower, but it's still good enough to not be the bottleneck for flow. Then I think it's only the economics that matter in that sense, right? So yeah. And of course, every individual operator has to look at those trade-offs. You have to look into models. We're testing our proppants, very frequently in longer-term connectivity test cells, all the local sands, and they, of course, do not compare favorably in connectivity compared to the white sands. But of course, what compares favorably is their economics. And if they're above that threshold where they're not the bottleneck for production response, then it's good enough. We went through this ourselves, right? I think even in this graph that I'm showing right here on the screen by accident, all the red lines here have we actually pumped ceramics. We thought that, connectivity in this case, we had to be significantly over that threshold of what is good enough. We thought that ceramics were needed for that. But then in 2014, when Saudi Arabia, cut oil prices, some operators that we were pumping for with this plug-and-perf slickwater ceramics design said, why don't we do exactly the same, but we're pumping white sand instead? And to our astonishment, there was hardly a change in production. And, of course, that's then a 5x cut in price for your connectivity. And I think some people are still making that trade-off today with local sand, where they see, very little impact in, relatively, at least in the short term. We'll see in the long term, but that's why I think that trade-off is important.
Excellent. We actually are right.
Leen, as always, what a wonderful presentation. It's always so good to hear from you. I'm glad you're still actively involved.
Ali, so good to see you. Thank you so much for the kind words.
No, this was excellent. I learned a lot. Thank you.
All right.
Thank you so much.
We are right on an hour. I mean, do you have a few more minutes because I have several more questions, or do you need to go?
I have all the time in the world.
Thank you. So I think the next one is very interesting. I mean, you're gonna really like it. So the next one comes from Eric Schmelzel. I mean, I'm sorry if I didn't pronounce it right.
Yep.
So with most of the prime drill locations in the major basins already drilled, and the steep decline associated with shale production, how do you see the energy production levels over the next few years? Is the USA on the brink of a steep and irreversible production decline?
Oh, hey, great question, Eric. Good to hear from you, man. I hope you're well. If anybody can predict that, I wouldn't be it, I think. But I can give you some thoughts, I think. So I certainly think that, of course, with the price reduction that I've showed, right, and the lower break-even costs and things like that, tier one acreage is really, tier two acreage is becoming tier one acreage, and kind of I think as an industry can move to areas that we previously thought were maybe not economical with all the lessons we've learned. And I think there's a lot more potential to be had, right, by going to these, I think, the apples are a little bit higher up in the tree, but I think we can get to them now. And so, with, I think, these technology changes. Also, I think, I do agree with you, Eric, that if you look at two metrics, the metric of production per well, I think that's about at its height, right? I think there's maybe more things we can do, but you can see actually in my next graph, I think, right? So the production per well is on top, and then the production per foot is below that. And you could argue that production per well is actually peaked, and that production per foot is about to peak, or maybe has peaked just recently. But of course, the production per dollar spent hasn't peaked yet, I think. So, right, I'm not showing you that, but I think, I should show that as well in a future graph. That's, of course, the one that matters. right? So we cramp a lot more stuff into a foot, as I showed you, and that's, I think, helped to keep that production per foot up, but just barely. And now, of course, the countering forces are, there's well interference. In some cases, there may be somewhat of a depletion effect. We are going to acreage that is not as high quality as what we fracked and drilled before. But these things are very, very, very slow moving. And again, the thing that matters, the dollars per barrel, that's still going down, I think. So, or at least stabilizing. So I think we have a lot more running room. And, we can go elsewhere. And there are many, many other places in the world where, they could benefit from all these advances we've made.
All right, thank you. So the next question is from Sean, and I'm not gonna even try to pronounce the last name. So, so can you please comment on the role of fracture diagnostics, such as fiber optics, strain measurements, microseismic tracers, and so on? How do they contribute to the cost reduction?
Yeah, of course, that's a question dear to my heart. I was, in the diagnostics industry for a long time, and I thought, it was at key moments where you needed your eyes to see what's happening downhole with fractures, right? And even if it's an incomplete picture, there is a place for diagnostics, and and often, maybe in the beginning, more frequently than today, for when you're doing a pilot, when you're testing certain things. But also, and I didn't realize this until recently, but some of the cost of these diagnostics have come down tremendously. So I think there's place for more use of it, and I think especially, a realization that this disposable fiber, for example, you can have a cup, a coffee or water cup filled with, miles and miles of fiber that you can just pump down, roll out, and interrogate, in multiple wells around an area that you're fracking. The cost to do so is very, very small. And when you're done with your project, you just let the end of the fiber, you just let the kind of kite fly out and let the side you're holding go. And it's a cup of fiber that's your disposed material. And I think there's more promise in some of these things, quite a bit lower cost. There's other costs like pulsing the well, interrogating it for better understanding the connection between the near wellbore and the far field, things like that. That together, I think, can provide somewhat of a picture as well of what's going on downhole. I think diagnostics are key, but I think our industry has been so keen in reducing cost, as and of course that's what my presentation is about. That's I think why it's not used as frequently as maybe nerds like myself would like to see it, but that's a cost consideration. But again, I think diagnostics are also helping. As the cost of diagnostics come down, there's maybe more opportunity for them as well. But I certainly think the early. Chris Wright calls it the map that changed everything. The realization that you're creating complexity in Barnett Shale frac jobs when you're doing slick water versus something else was one of the kind of an eye-opening moment, I think, for our industry that got us all started.
If you think about what we know about fracturing today versus what we knew about it 20 years ago, what has made the difference are these diagnostics. And in my view, this is an activity that needs to continue. And the more we know about what's going on downhole, the better we can increase the effectiveness of the fracturing operation. So I think diagnostics are very important, and we need to continue focusing on it, and even find better and more efficient ways of finding out exactly what is going on downhole.
I agree, Ali, but it ultimately is an economic question as well.
But economics is highly dependent on the volume of oil that you produce.
Yep.
And anything that increases that volume and efficiency of the operation improves the economics.
Yeah, I agree with you.
Right. So we have the next question from Hervey Vigor, I guess. So the question is about pad design. So what is the optimal pad size in terms of how many wells, and how often SIMOPS are used on these pads?
Yeah, I think there's no good answer for that, but because it depends on so many different things. But I think in general, and I think we didn't really talk much about the future, but one of the things I think is that pads are increasing. Here in the DJ Basin, we talked about our Sankey diagram and how much time we're pumping. One of the ways we've really improved that here is that there's so many wells on a pad, sometimes 20, 30, 40 wells on a pad in the DJ. And one of the reasons is, of course, that we have nearby population. There's cities nearby, and we want to minimize our footprint as much as possible. And drill longer laterals. They're drilling 4-mile laterals from a single pad. So the benefit to that for us is that we're on a location for like half a year, fracking 20 wells, and but that's not for every operator, right? Because you need to kind of, that delay between drilling and fracking is now significant, because if you can't allow SIMOPS on your pad, you need to be done with all these wells before you frack them all. Of course, that's quite a working capital that you have at work in those cases. So that's not for every operator, but I think and there were service companies, giving example in California, of all places, for fracking. But I worked there, in my early career, and Halliburton actually was pumping in some of these relatively shallow reservoirs in Lost Hills and Belridge, and actually having a central location for their pumping services. They wouldn't move. They would just lay out line. Now, and these are the very peculiar situations of very close offset wells in these fields. But they would just lay line to every well or pad, even up to a mile or so away, and frack it at relatively low pressure. So there were very favorable circumstances to do it for them. But I think our industry will move that direction a little bit as well. We rig up somewhere centrally, bury pipe, and frack through it to a location that's 2 miles away. And of course, then, and there's a whole group of people that are building infrastructure associated with doing that. But it would allow us to, be in one place for a much, much longer time. The nuisance goes away from, of course, proppant trucks that are delivering boxes and things like that. That is still a real, I think, eyesore for people living around it. If you set up shop, in an area where almost nobody lives, that's better for everybody as well. So I think, that number will increase, and I think frac operations will become more centralized, and more kind of more of an industrial project, if you will, maybe more permanent industrial location than what we have today. Of course, it doesn't work everywhere, so lots of other things need to happen, but I think that's the trend.
All right, so I have a few more questions. I think the next one is a really interesting one from Thomas Smith, right? So we just heard about this amazing achievement of fracturing community related to shales, right? But what is the next big opportunity, in your opinion, for the industry, right?
Well, I think, that one other thing that I want to highlight, a lot of companies, and this is also scaling, a lot of companies are doing fracking into 2 or 3 or 4 wells at the same time. Again, this is just for the big guys, because of course you need to have lots of wells available to frack. But the benefit is that, one of the wastes in our industry is that when we're pumping down a well, we have to overcome friction. And in, very simplistic terms, friction is proportional to the rate squared. Not quite, but almost. So if I'm pumping 4 times faster than I used to pump, or 10 years ago, or if I'm pumping 2 times faster than, say, 10 years ago, my friction, wellbore friction, is up 4x, right? The square of that, roughly. So I'm overcoming that, and that's a ways to overcome. So what are some companies doing? They're actually pumping at a somewhat faster rate, but into 2 wells at the same time. They're cutting the stage length. They're cutting the perf cluster that they're serving per well, but they're increasing the perf clusters that they're serving for all wells combined, so at a higher rate. But what that does is it dramatically cuts that friction component on a per well basis. So more of the horsepower used by us is actually directly transferred into creating fractures downhole instead of overcoming friction, right? So that's, I think, a good development. And I think, as far as other development go, of course, what we do with everything that we do, we're only producing 10 to 12 to 14% of oil in place. We need to get to, and some of our operator customers are experimenting with that. What is the secondary recovery mechanism in all these different basins? What do we need to do to get to the other 85, 90% of oil in place, over time? And that's a huge prize. And I'm very hopeful. I just wrote about this on my blog, that I'm hopeful that geothermal energy teaches us some of the ways of what needs to happen with secondary recovery in oil and gas shale wells. Because I think, sweeping that area between wells, an injector producer or huff and puff mechanism or whatever, we need to get to a higher production or a higher recovery ratio.
All right, so we have 3 more to go. So well, and thank you so much for your time. So so the next one is, I mean, and apologies, I skipped a few comments, right? So focus on questions. So the next one is from Adrian Morales. Like, in your opinion, has the average completed lateral lengths reached a plateau, or do you still think that it's still increasing? Right, so the lateral lengths, do you think it's kind of reached lateral lengths or not?
I think it's still increasing. I'm not a driller, but I think, we're pushing all the time what we can do to clean out the well with dissolvable plugs. As I mentioned before, I was on a location just a couple of months ago here in the DJ, just slightly east of Denver, where they were drilling 4-mile laterals. No problem whatsoever. They're pushing it. I think in Appalachia, that's a common thing to do. 20,000-foot laterals. It is. If I look at the trends, I didn't show it here, but it seems we're easily adding 400 feet every year to our lateral length. I see no let up in reduction. There's still a lot of reservoirs where it's lower than that, but it's increasing everywhere. And I think it's a bang for the buck, if you will, and with the fact that drillers are drilling 3 times faster than they were 10 years ago, their costs are down significantly as well. I think, I don't see really a downside. I want to maybe there was somebody in a town hall, years ago, complaining about drilling companies nearby, etc. And they said, this was north of Denver, and the drilling company was actually south of Denver. They said, why don't you drill your wells from there? Well, it's about 30 miles, not really possible. But who knows, in the next 100 years, maybe we'll be able to drill that far. And maybe with a different way, marrying tunnel boring to drilling or whatever, and making it economic.
All right. Well, next question is from Mohammed Badgaish, I guess. Apologies if I didn't pronounce it right. So as we increase the number of frac stages, right, and the laterals, right, what can you say about the lost footage of these horizontal wells, right? So what's kind of, I mean, like we have some unproductive stages, unproductive footage, and does it increase, or do you think it stays about the same?
I'm not sure I understand the question. I'm sorry.
Oh, so as the number of stages increases and lateral length increases, right? So we expect to have some unproductive footage, right, along the lateral. So do you think this unproductive footage increases with the length of lateral, number of stages, or not?
Yeah, I don't know very well. You know, I'm sure there is some. I always thought, you know, that, you know, a next question may be then, you know, are you not, should you not frack your unproductive footage or what you think is unproductive because some log measurement or, you know, drilling measurement. Um, I often think, you know, that's what happens near the well itself. Maybe you do know, but you know, what is the reservoir around it? It's hard to know. So I've always been a proponent of maybe frack since you drilled it already, frack it as well. But I do not know, you know, yeah, I don't have enough information. I'm sure operators will have fiber optic data, you know, where they can say, you know, yeah, maybe these areas don't contribute, but it could very well be the frac, you know, or something peculiar on the geologic side as well. So I don't know that I'm not the right person to answer that question, Igor. I'm sorry.
That's okay. That's okay. It's excellent. Thank you. And the last but not least,
That
from
that situation is always there. We perforate the areas and we inject fluid into it, and we assume that every perforated interval is fractured. The reality is that they are not all fractured, and there are the areas within the well which are not being fractured, and so unproductive areas are always going to be there. It's part of the operation, my view.
Yep, good point.
Thank you. And the last but not least from Nabil, right? And so this kind of like a little bit of maybe cause some discussion, but let's try to keep it you know, pretty short. So I don't know if you attended like a few weeks ago, we had a debate between Mark McClure and Ahmad Gassemi whether the hydraulic fractures are planar or complex. And so the question is, what do you think? So do you think the fractures are complex or the fractures are mostly planar?
Nabil, thank you so much for the question. I hope you're very well, man. That's I'm going to give you a double answer here. I've seen fracks in the lab. You know, I've been a lab nerd. You know, back in my days at Delft University of Technology, and of course, what you see on a very small scale, and even, you know, on a maybe somewhat larger scale of, you know, several feet or whatever, some of the core throughs and mindbacks that Dr. Norm Rapinski did, you know, you see that there's complexity to fracking, and it's always puzzling because people think, you know, to minimize energy. To minimize the amount of work done by, you know, equipment, at some point it needs to be a single, very simplistic fracture, right? But I think the heterogeneity, the small scale heterogeneity in rock, I think, is always messing that up. So I think there is complexity kind of on that very small scale of inches and feet, if you will. But then if you go to a larger scale, and I often like to talk about the big picture, what is the big picture fracture doing? You know, even in Dr. Warpinski's work, you know, core through and mindbacks on the western slope in Colorado, he found that, you know, yeah, there's complexity within a relatively narrow area, right? So the fracture orientation and, you know, overall zone of fracking is relatively planar, right? It's maybe a few feet wide, but in that few feet, I find a few to a dozen, or maybe, you know, a few dozen in this case, fractures, you know, within a few feet from each other. I think, you know, because fractures are starting, then they're stopping, then another one takes over, and that's actually on that per foot scale, if you will. So creating the local complexity. But then if you look at the thing from, you know, 30,000 feet high, it looks like a planar fracture. Maybe the feature is a few feet wide, with multiple fractures that are complex, but the big structure is simple and planar, or more or less planar, with a length that's hundreds to thousands of feet, and a height and a width that is distributed over a bit of a complexity, a complex fracture system. That's a kind of my dual answer.
Excellent.
Yeah, you need to consider another variable, which is generally not being you know, looked at deeply, and that is, as we fracture these horizontal wells, each fracture changes the state of stress for the next fracture. Although the
Absolutely.
created fractures are planar on a scale, just exactly as Leen said, which I completely agree with, but they are not parallel with each other. And at some point,
Yep.
the minimum principal stress may completely change so that the fractures that you create are not perpendicular to the wellbore, and they could very well be in a different direction. So that is a dimension that needs to be considered, especially in these long horizontal wells. You know, you're talking about 2-3 mile long horizontal wells. The state of stress changes definitely as we move down the length of the well.
Absolutely, I second that, Ali. And of course, I think that's a self-propelling success story a little bit as well, right? Because if you do create these multiple planar fractures right next to each other, at some point you're impacting the state of stress so much that you're overcoming the stress differential between, say, two horizontal planes, and you're creating other components, fracking down other orientations. And that's where, for instance, a technology called surface tilt fracture mapping often found that, even though maybe these fractures, we think of them kind of in the large scale as planar, there's a component opening, of course, most of the component opening kind of perpendicular to the main principal stress, but there always seems to be another component, debonding layers that have been laid down geological wise, and also against that minimum principal stress, or the orientation perpendicular to that, the intermediate stress, if you will, where there's some opening as well. And it all, I think, contributes to kind of an area that can help, produce hydrocarbons, and adds to the complexity of the whole system.
Excellent. Excellent. I think I have only one thing to add, I guess, here, if I may just take another 10 seconds, is that, one thing that you may also want to consider is inflation. Because if you can't, because $1 in 2010 and 2024 buys you, a whole lot less. And so if you account for inflation, though, actually the achievements is going to be, much more striking. So I think this is, also a really important factor. But I think we ran out of questions. So thank you so much, Leen, for your time. So we took extra half an hour, but as you see, we had a very, very lively discussion and very, very interesting questions. So thank you a lot for your time and for your talk.
Thanks for having me, and I really appreciate the engagement, and good to see many old friends. Appreciate it.